These two functions have been drawn so that they have the same slope everywhere, but clearly they're not the same function. And you could notice that if you took the y-coordinate of that point and subtracted the y-coordinate of this point, since they're on the same vertical line, their x's are the same, so the distance between them is just the difference between their y's. We've been told that we're going to call that value c. And it turns out that if those 2 points have those 2 functions have the same slope everywhere, then every time we subtract the 2 y values that go with that correspond to one x value, we're going to get this same value. In this case, we've called it c. But these functions have the same slope everywhere, which means they must have the same derivative. So this is a big idea here. If you have 2 functions that have this same derivative, they don't necessarily have to have been the same function to start. They could be the same function except with this difference of a constant. So imagine this. This is not hard to imagine. What if I said, well, let's call it f of x equals x squared. And I said, hey, what's f prime? You're like, oh, that's easy. F prime equals 2x. What if I said, here's another function g of x equals x squared minus 9. You can't see that, but it says x squared minus 9, and I asked you what's g prime? You're like, oh, that's easy. That's 2x. So notice these 2 functions have the same derivative. That doesn't mean that they started out as the same function. This has a big old plus 0 on the end. This one had a big old minus 9 on the end. Just because we have 2 functions that have the same derivative, we don't know that they were the same function to start. So we have to talk about what an antiderivative is. Hold on. So I hope I've said this to you before. Every time you learn something new in math, and you learned first about addition, and then you learned about subtraction. Addition and subtraction are inverses. We learn about them at approximately the same time because it's easier to understand one once you know the other. But you learned about logarithms, and then learned about exponents, or the other way around. They undo each other. They're inverse functions. Well, we've been learning about how to take a derivative. The inverse of taking a derivative is called finding an antiderivative. So, and it turns out that's going to be the whole topic of second semester. So, most of second semester. We want to understand what that means. It's really, you could probably do it in your head for at least some of the functions. It's just finding a function that has the derivative you want. Right? So, here's a formal definition. An antiderivative. A function capital F of x is an antiderivative of little f if capital F prime is little f for all the x's in the domain. Nobody's going to try to trick you, I don't think, with domain. And this process, this thing we do to try to find an antiderivative, it's called antidifferentiation. Here in chapter 4, we're going to do some that you can kind of do in your head. Sort of undoing, you sort of checking through the list of all the derivatives you know by heart and thinking of one that's the right antiderivative. And then second semester, we're going to learn lots of techniques for finding more trickier ones. Okay, so now that you know what an antiderivative is, it's just a function whose derivative is the function you started with. So let's go back up here, and there's a question on your paper. Can you find any antiderivative of sine of x? So you actually have this is the thought process you have to have, and pretty soon it'll come really fast, but at the beginning it takes a little while to do. So you have to ask yourself, what function could I take the derivative of and get sine of x as the answer? So probably, I'm guessing, this is the thought process you have. You're like, oh yeah, sine and cosine, they're, derivatives of each other. So you stop and you think, is it cosine? So you ask yourself, do I take the derivative of cosine and get sine as the answer? No, you don't, because if you try to take the derivative of cosine, you would get negative sine as the answer. So you're going to have to adjust that slightly in your head. You're like, oh, well, what if I tried taking the derivative of negative cosine of x? And you've found one. So capital F of x, this is sort of it's a convention we use It's not exactly formal, but if little f is a function, you can use capital F for its antiderivative. Capital F of x could equal negative cosine of x. Now notice there are actually infinitely many correct answers. The derivative of negative cosine of x is in fact sine x. So this is a correct answer. But I could take the derivative of negative cosine of x plus 9. The result is sine of x, which is what I wanted. So this could be plus 93. This could be plus 93 pi minus e. There could be any constant added on at the end or not. You were just asked to find any antiderivative, any function whose derivative is sine of x. So you found one. We'll go back to this version. So in order to acknowledge this idea that when we find a derivative, we can actually find an antiderivative. We can actually find a whole family. We know that functions that have the same derivative differ by a constant. So, well, this answer is totally fine because I asked you to give any antiderivative. What's common practice is to write that capital F of x, the antiderivative of sine x, is equal to negative cosine of x plus a constant. And we have all agreed to use capital C to stand for this constant, something that's added on. So when it's time to answer a question like this one, this one's not on your handout, but it's a warm-up for the problem that is, what if I said, find the function f of x, whose derivative is sine, and whose graph passes through 0, 2. So this is a way of saying I want little f to have a derivative of sine. That means I want little f to be the antiderivative of sine. Well, we just said a second ago, a little bit confusing because then I used capital F. Here I've been asked to use little f. I'm going to let little f of x be negative cosine of x plus a constant. This is an expression for all the possible functions in the whole world whose derivative is sine x. But I have this second piece of information now, which is going to help me figure out what I should let c equal. And the problem that was on your paper, we didn't have any other information. We were just asked to find any antiderivative. So we left the plus c on the end. But here, we have one more piece of information. This can help us a lot. We want the graph to contain, this is an ordered pair, 0, 2. And just notice that. Let's be very careful about noticing this. The input, the x is 0, and the y is 2. So, and y is the same as f of x. So we can do what's on this paper here, which is I'm going to replace the f of x with 2. I'm going to replace the x with 0. And here's what I have. I'm going to have 2 is equal to the negative cosine of 0 plus c. That tells me 2 equals, the cosine of 0 is 1. I'm supposed to make it negative, so this is going to be a negative 1 plus c. I can solve this equation for c. I'm going to add 1 to both sides. I get 3. That's a 3 equals c. So my final answer, this function I was looking for, whose derivative is sine and that contains the point 0, 2, is f of x equals negative cosine of x plus, I don't leave the c in my answer, I went the next mile and figured out that c is 3. So here's my final answer. The function I was looking for, they asked me to call it f of x, is equal to the negative cosine of x plus 3. So go back to your paper. We've been asked to find the antiderivative of f of x equals sine of x, for which capital F of pi equals 7. So watch this. Let's get bigger. There we go. I know so far, I've been through this part where I try to figure out the antiderivative of sine, and I know it looks something like this. It's got to be negative cosine of x plus something, which I'm going to call c. Here I've been given an ordered pair. The x is the pi, the y, the output, the capital F of x, is equal to 7. So here's the equation. I can write 7 equals the negative cosine of pi plus a constant. I'm just going to keep moving down this direction. So 7 equals, the cosine of pi is negative 1, and then I have a negative in front. So negative, negative 1, positive 1, plus a constant. That tells me that 6 equals C. My final answer, capital F of x equals zip, negative cosine of x plus 6. This process of finding an antiderivative, is going to come up through the whole rest of the class. If you were asked to find an antiderivative and you have this one extra piece of information in the last two problems, it was an ordered pair, that's called an initial value problem. We've been given some value on the function we're trying to find, and that helps us go through that next step to figure out what C is, and we can give our answer here, this final function, without a constant in it. All right, this last example, we're going to combine what we found out, what we learned in 4.1 with what we've learned in 4.2 here, to find the extreme values, relative extreme values of a function. We need to check out critical points. So critical points, relative extreme values can occur at places where the derivative of this function that we're trying to describe are equal to 0 or are undefined. So I'm going to start here. I've been asked to find any relative extrema of f of x. So I'm going to be checking for places where f prime of x equals 0. F of x is polynomial. So f prime of x is also going to be polynomial, and polynomial functions are never undefined. They don't break any of those rules. They give us like a hole in the domain. So this part's going to be pretty easy. That's an equal sign, not a colon. So f prime of x equals 5 minus 2x. I want 5 minus 2x to equal 0. And that's going to happen when x equals 5 halves. You will find that the next part where we tested a point sort of on either side to figure out if the function was going up and then coming down or going down and then coming back up, that's going to be simplified by this next part, which is to figure out on which intervals f is increasing or decreasing. So we're going to hold on the answer to part A and work on the answer to part B. Part B, where is the function f of x increasing? Well, anywhere f prime is positive. So I'm going to write f prime is greater than 0. That's 5 minus 2x is greater than 0. We're going to end up with negative 2x. Negative 2x is greater than negative 5. Ooh, tricky. I'm going to have to divide by negative 2. Negative 2, I'm going to get x is less than 5 halves. So why didn't I have to factor? I didn't have to factor because I have a degree 1 inequality here. You could go through that process of making a sign chart, but it's not going to help us any. My function f is going to be decreasing. Nope. I was answering part B. Solving f prime of x is positive. So my function f is increasing when x is less than 5 halves. You can imagine what happens when I try to solve f prime of x is less than 0, and to find that that's true when x is greater than 5 halves. So I hope you will always consider bringing this back to a visualization of what's going on. You know enough about f of x to have answered this question without any calculus. F of x is quadratic. It's not written in standard form, but you could rewrite it in standard form. You notice there's a negative leading coefficient. So if you were to graph f of x, it would be, if you don't mind my using the colloquial language, an upside down parabola, right? So it's going to increase up until its vertex, and it's going to decrease sort of after its vertex. Is it going to have a relative maximum? Yeah, it's going to have a relative maximum at the vertex. Is it going to have a relative minimum? No, an upside down parabola doesn't have a relative minimum. So let me erase sort of this work and write up my final answers here. All right, so notice I've written these up sort of in a different order than they were presented. F of x is increasing on negative infinity to 5/2 because f prime of x is positive on that interval. F of x is decreasing on 5/2 to infinity because f prime of x is negative on that interval. And we decided f of x is a relative maximum at x equals 5/2. The only place we have to check is a place where the derivative, f prime of x equaled 0. That happened at 5/2. And at 5/2, we thought about the picture. If you want to not think about the picture, if you want an algebra, sort of algebra calculus way to write this up, that's what's coming up in 4.3. That's the big idea in 4.3. So there is this assignment printed at the bottom of your page. I'm not sure if when I gave out your assignment I revised that or not. So this is, if I gave you an assignment when I handed out the most recent copy of this page and you prefer it, feel free to do it. Otherwise, page 202, number 15, 17, 31, 33, 37, and if you would please do your best on those problems before you come see me in class.